Okay, so you're given a solution, and you're going to react that with another solution. You're going to pour them together and get a total. And the outcome is taking place in a solution phase reaction. Let me think. The essence of this and the focal point of this is to show you how the calculations are the same as those that we've done when we use solid-solid or mass-mass relationships. The idea is, how do you take solution data and convert it to moles? So convert solution data to moles and solve problem. Solution data is two parts, molarity and volume, connect together. For example, 25 milliliters of 0.28 molar hydrochloric acid. This is aqueous solution. This is solution data. Now, if you see that in data given in a problem, moles is always molarity times volume expressed in liters. So in this case, moles of HCl is the molarity 0.28 molar, which is again moles per liter, times volume of 25 mils, but you have to express that in liters if you're not working with the dilution equation. If you're working with a reaction equation that you made, I will get to that. Because this molarity, moles over liters, liters will cancel, and so you're left with moles. So this is 0.0070 mole of HCl in that issue right there. Well, converting to moles is simply molarity times volume in liters. We'll just pick up and do this right here. Okay, so the question is, out of this, how much silver chromate will be generated in grams if you mix this together? Two things have to happen here. You got to convert to moles and determine if one of them is a limiting reagent or not, and then use the limiting reagent to define how much you're going to generate in moles, and then times formula weight to go to grams. So the reaction is simply silver nitrate, aqueous, plus, I'll spread it out, plus the potassium chromate, and you should recognize a double replacement by now. And so the outcome of this is, I'll put the potassium nitrate first. Let me make that look more. And then you have your silver chromate, and that's your driving force, and that's what we're looking for, the precipitant. Now, what I mentioned yesterday is the best thing to do is set up a flow of calculation surrounding only the reagents that are undergoing reaction. And the ones that are undergoing reaction, obviously, are the silver nitrate and potassium chromate. So what I suggest is, say, take 150 milliliters of 0.5 molar silver nitrate and write this down in this format. Like that. And then convert to moles. Well, how do you do that? Remember, moles is molarity times volume in liters. So we want to convert the 150 to liters, and so that's moving the decimal 3 places to the left. So I would have 0.15 times 0.5, and that's now in moles, because the molarity times volume is moles, and that's silver nitrate. And then this is 0.10 times 0.4 mole of the K2CrO4. Now see how simple that is? If you'll keep that organized like that, you can manage these, because you can move it right into the moles and you can see immediately what your reaction ratios are. And of course I didn't balance it. Let me balance this. What is it? 2 potassiums and a couple of nitrates. So I gotta have 2 over here, and we already got 2. So there you go. So that's balanced. And so you take that and convert it to moles. 0.15 times 0.5 equals, it's 0.075 mole of the silver nitrate plus mole of K2CrO4. Okay, now converted to moles. Now, which is the limiting reagent? Well, moles divided by the respective coefficients of those of the balanced equation. The smaller number is the limiting reagent. So we want to take 0.075 divided by 2, and we want to take 0.040 divided by 1. And of course that gives, of course, 0.04, 0.075 divided by 2, 038. And so the 038 is a smaller value, which is your limiting reactant. So what this tells us is that when we work this problem, we need to work it from the moles of silver nitrate to produce moles of silver chromate. And you can see it's a 2-to-1 reaction ratio. So since the number is going from 2 to 1, that's a smaller number. So essentially whatever moles we have would, 0.075. Remember, you have to go back up here. This is only a technique for identifying the limiting reagent. So you want to move back up here. Don't get caught using that number. So it's 0.075 yields X moles of the silver chromate. Well, it has to be a smaller number than 0.075, right? So by how much? Well, you take the coefficients and set up a ratio that will make the 0.075 smaller number. So in the solution of this, silver NO3, 2 moles of that, plus K2CrO4 goes to the 2 KNO3s, plus silver chromate. We have 0.075 mole, and we ignore the potassium chromate because that's going to be in excess. It's not the limiting reagent, and we ignore that one because that's not part of the problem. And so the question is, how many moles of the silver chromate will be generated? Well, it turns out that this is 2 to 1, so I need 1/2. I need of the 0.075. I need a smaller number, which is 0.038 mole of the silver chromate, because it's a smaller number than the 2 over here. We're in a balanced equation. Now we need the formula weight, so the grams of Ag2CrO4 is equal to the moles times formula weight, and of course that's 0.038 mole. So we got 330 grams per mole, but in the problem we only have 0.038 moles, and so when we make our final computation, I get 12.4 to 3 sig figs. Of course, that would be a precipitant. I don't know what the hell, they got 12.4 out of it. So, do you see the flow of the problem? See, now I took the reactants that are actually reacting and attached the solution data, and then worked them into moles, and then related it to the equation. Once I found out the limiting reagent, then I worked the problem from the basis of the limiting reagent, and it's a 2 to 1, so it has to go down in size, so it's half of what's given over here is the amount generated over here, and so that works out to 12.4 grams. Okay, this next example is based on this equation. All of it's in solution, aqueous solution. This will be your precipitant and 2 aluminum nitrates. Alright, let's see what we're given. So it's asking how many milliliters of the barium nitrate, 0.28 molar of the barium nitrate are required to precipitate as barium sulfate. All of the sulfate ions from 25. Okay, so over here you have 25 milliliters of 0.35 molar. Okay, so yeah, you're going to make so much barium sulfate from this interaction because it's a double replacement. Barium hooks up with the sulfate, aluminum certainly hooks up with the nitrate as shown in the reaction. Now what the issue is, how many milliliters here? Now there are a couple of ways to work this. We can take this and use the technique we used before, where we take these, convert them to moles, and then look at how much mole-mole relationship. But when you look at this, what do you see? We have a reaction here. It's 3 moles of the barium nitrate reacting with 1 mole of the aluminum sulfate. That's what the equation says, right? I mean, you see that point blank. So we can honestly say that the moles of barium nitrate is greater than the moles of aluminum sulfate. Everybody agree? However, I can get an equation out of this. how would I go about making the moles of barium nitrate equal to the moles of aluminum sulfate? How would I go about? I can swap the coefficients. Put a 1 over here and 3 over here. Think about that. It may be skewing your brain a little bit. But right now, this is 3 times larger than barium nitrate than aluminum sulfate, right? So if I happen to have the moles of aluminum sulfate in whatever they are, and I multiply it times 3, wouldn't it be equal to the amount of barium nitrate? Yes? Does everybody see that? You're going to need it. I hope you do. We know that moles is equal to molarity times volume expressed in liters. Now, if both sides are the same expression, you can leave that in milliliters. So, put molarity times volume here and here, 1 times molarity times volume, and you can leave that in milliliters if you want to. Now put milliliters down here. And that, of course, is the barium nitrate is equal to 3 times molarity times volume in milliliters of the aluminum sulfate. And I'll move that back over here and make it neat. Like that. So what data have we been given up here? So we go back, and after we say set those equal to each other, molarity times volume equal molarity times volume, swap the coefficients. And so the data that I'm given is the volume in milliliters is the unknown times the molarity is 0.28 molar is now equal to 3 times the molarity of the aluminum sulfate, 0.35 molar, and the volume is 25 milliliters. So you can see real quick, solving for the volume in milliliters now leaves us with the answer to the question we were asked. Molarities drop out, we're left with milliliters, and I don't know if I can get all of that on the page or not. Yeah, maybe I can. Yeah, there you go. So just relating these two in terms of molarity times volume of this one and molarity, that's moles and moles. That's what I've done, moles and moles. And I made them equal by simply swapping the coefficients. Now you're going to have problems where one side is given in moles and the other is given in solution data. What volume of, say, barium nitrate solution would you need to completely react with whatever number of moles of silver of aluminum sulfate you would need? So you still use the same mole-mole relationship and swap coefficients. Now the easiest one, of course, is if they're 1-to-1. You use molarity times volume of reagent 1 equals molarity times volume of reagent 2. And you put in the data and solve for the unknown. Those are acid-base type reaction systems. Okay. Here you're given the HCl aqueous plus NaOH aqueous goes to NaCl, and that's the solution, plus the driving force is H2O, and it forms a liquid. And so what you're given is a question, how many milliliters of 0.4696 molar of the HCl is required to neutralize 20 milliliters of the 0.809 molar sodium hydroxide. And so if you look at the equation, what are we looking at? 1 mole, 1 mole, so that's a 1-to-1. So 1 mole from equation, 1 mole HCl uses 1 mole sodium hydroxide. Well, what does moles equal? Molarity times volume. So then molarity times volume of the HCl has got to equal molarity times volume of the NaOH. You don't have to swap coefficients. Well, yeah, you swap ones, that's fine. So 1 and 1, right? And then put in your data. So your volume of HCl needed in a 0.496 molar is equal to 0.809 molar times 20 milliliters. Now you do not have to change the liters here because both sides of this equation have the same units. Now if one's moles and one's not, then you have to use liters. Okay, so volume of HCl in this one is 0.809 molar times 20 milliliters divided by the 0.496 molar. Molarities drop out, and you have an answer. $32.6 is what I get. Doesn't have an answer to it, but I'll defend that answer to the death. I don't have the answer to it. Now, corrected. But anyway.